What if space itself could fold and touch another part of the universe? What if the stars above were not just distant but secretly connected through tunnels carved into the very fabric of reality? Good evening, and welcome to the Sleepy Astronomer. Tonight, we're drifting through one of the most fascinating and puzzling ideas in all of physics, the possibility of wormholes, the cosmic shortcuts that might, in theory, bridge impossible distances. Before we set out, I'd love to know, where in the world are you watching from tonight? I'm always amazed to see this little corner of the universe filled with listeners from so many different places. If you enjoy these calm journeys through space and science, please do give the video a like and subscribe if you'd like to join us for more. And to those already subscribed, thank you. You're helping this quiet community of sleepy stargazers grow with every video. I do hope this episode isn't too interesting and keeps you awake, but if it does, at least you might learn something truly strange before you drift off. So settle in. Let the lights dim and the noise of the day fade, because tonight we're asking a question that bends both space and imagination. Are wormholes real? When Einstein first realized that space and time were woven together into a single fabric, even he could not have predicted how strange that idea would become. Gravity was no longer a force that pulled. It was a curve in the geometry of reality itself. And in those curves, hidden deep within the mathematics, lay the possibility of tunnels, connections between distant parts of the universe that might, for an instant or forever, bring faraway worlds close together. Physicists would later call them wormholes, a name that feels almost playful but conceals some of the most serious mathematics ever written. The notion began as a curiosity within general relativity, a side effect of equations too elegant to ignore. It suggested that space-time might not be a smooth sheet, but a landscape that could, under extreme conditions, fold and loop back on itself. Over time, this idea has wandered from the chalkboards of theorists to the imaginations of storytellers, from Einstein and Rosen to science fiction films and bedtime musings about where such passages might lead. Yet behind the fantasy lies a question grounded in genuine physics. Could the universe truly contain such gateways? Could gravity, in its deepest logic, allow space to connect across impossible distances? In this calm exploration, we'll follow that question wherever it leads. We'll trace the birth of the idea from Einstein's early work to modern research that tests the limits of relativity and quantum mechanics. We'll see why wormholes seem to require matter stranger than anything we've ever touched, why most would collapse in an instant, and why, even if none exist, studying them helps scientists understand how space and time themselves hold together. It's a story of theory more than discovery, but one that reveals how science dances with imagination. Because sometimes, the universe's most extraordinary mysteries are not hidden among the stars, but inside the equations that describe them. And so tonight, as you settle deeper into rest, we begin our quiet journey into the folds of space-time, to see where curiosity, mathematics and wonder might meet. Space and time, two words that seem so ordinary, yet they describe everything that has ever existed. Every planet, every atom, every moment of your life. For most of history, people thought of them as separate things. Space was where everything happened, and time was when it happened. One was the stage, the other the ticking clock that kept the play moving. Then came Einstein, and suddenly the curtain lifted to reveal that they were not two actors at all, but one continuous fabric, a single entity called space-time. It's difficult to picture something like that because it doesn't behave like anything we can touch. You can't pick up a piece of space-time or fold it into a neat square. But if you imagine it as an invisible landscape, one that stretches across the cosmos, you can begin to sense what Einstein saw in his equations. Every planet, every star, even you as you sit here, are resting on that landscape, pressing into it ever so slightly. Think of a smooth rubber sheet pulled tight. If you place a marble on it, the surface dips. Roll a smaller marble nearby, and it spirals toward the dip, not because the big marble pulls on it with some mysterious force, but because the surface itself is curved. That's gravity reimagined. It's not a force reaching across space, it's space itself guiding motion along its curves. The sun, with its enormous mass, makes a deep valley in space-time, and the Earth forever rolls around that valley. To us it feels like we're being pulled by the sun's gravity, but in truth, we're just following the gentle geometry of space. Even light, the fastest traveller in the universe, must obey that curvature. When light from a distant star passes near a massive object, it bends, tracing the contours of the cosmic terrain. Astronomers call this gravitational lensing, and they've seen it with telescopes. Arcs of starlight warped by galaxies billions of light years away, written proof that space-time is indeed a shape, not an abstract backdrop. Now, it's worth pausing on how revolutionary this was. Before Einstein, gravity was thought of as a force acting instantly across distance, a kind of invisible rope between objects. Isaac Newton described it beautifully, and his laws worked astonishingly well. But even he admitted he didn't know how gravity acted, only that it did. Einstein gave gravity a face, or rather, a geometry. He showed that matter tells space-time how to curve, and space-time tells matter how to move. If that sounds poetic, that's because it is. Imagine the universe as an enormous dance floor. The dancers, planets, moons, stars, don't pull on one another with invisible strings. Instead, their weight presses into the floor, creating dips and ridges, and each dancer glides along those curves. The floor shifts and ripples as they move, and those ripples are what we call gravitational waves. We've actually detected them, faint vibrations in the fabric of space-time itself, caused by titanic events like black holes colliding. These waves spread across the cosmos, whispering that space is alive and responsive, not the still void people once imagined. It's almost strange to realize that every second of your life you are moving through this four-dimensional fabric. 3 directions define space: forward and back, side to side, up and down, and time is the 4th. This steady progression of moments that keeps everything from happening all at once. Together they weave the stage on which reality unfolds. But unlike an ordinary fabric, space-time isn't flat and uniform. It can warp under the influence of mass and energy, stretching here, tightening there. That warping is gentle near small things like you or me, but dramatic around stars and black holes. Close to a black hole, the curvature becomes so steep that not even light can climb out, a point where geometry itself seems to break. It's as if the universe has twisted space and time into a shape we can barely comprehend. Yet that same twisting is what allows galaxies to form and planets to orbit. Gravity may seem ordinary, but it's the sculptor of the cosmos. Picture space as a rolling sea, where matter gathers, the surface dips, where energy flows, ripples travel outward. Most of the time, those ripples are faint, but in rare moments, like when 2 black holes merge, the sea shudders with waves so vast they pass through entire galaxies. By the time they reach us, they're smaller than an atom, yet still measurable. That's how sensitive our instruments have become, and how extraordinary space-time really is. If you could somehow step outside the universe and look back, you wouldn't see stars and planets scattered in emptiness. You'd see a great cosmic web, a surface that bends and flexes under the influence of every particle and photon. Where clusters of galaxies sit, the web dips. Between them, it stretches thin. It's a dynamic shape, constantly evolving, expanding, vibrating ever so slightly from ancient gravitational waves that have crossed billions of years to reach us. All of this paints a picture not of a static cosmos, but of one that's profoundly fluid. Space isn't just where things are, it's what things are made of in a sense, the stage and the story at once. And time isn't merely a ticking clock, but a direction woven into that same stage. You can't move through space without moving through time, and vice versa. The two are inseparable, forever joined in the great geometry of existence. And when you begin to see the universe in this way, something subtle changes. You stop thinking of gravity as an external force and start to imagine yourself riding the folds of a vast invisible landscape. Every step you take slightly reshapes that landscape, even if imperceptibly. Every planet, every atom, every beam of light leaves its mark. But here's where the imagination can't help but wonder. If space-time can curve, and if gravity can make valleys and hills in its surface, could it also bend so far that two distant regions actually meet? Could the cosmic fabric fold upon itself, allowing one point in space to touch another, a shortcut across the universe? That question, whispered out of the mathematics of relativity, opened a doorway not to another place but to another way of thinking. It suggests that space is not only flexible but possibly connected in ways we can barely grasp. And within that strange possibility lies the first glimmer of an idea so wild, it almost sounds like science fiction, the idea of a tunnel through space-time itself. In the early decades of the 20th century, physics was being rebuilt from its foundations. Einstein had already shaken the world by showing that time could stretch, space could curve, and that gravity itself was a shape rather than a pull. His general theory of relativity, published in 1915, was a masterpiece, a set of equations that described how mass and energy tell space-time how to bend. Yet Einstein was never content to leave his theory as abstract mathematics. He wanted to see what those equations could reveal about the hidden structure of reality. By the 1930s, he was turning his attention toward one of the most puzzling solutions lurking in his own creation, the black hole. At that time, physicists didn't even call them black holes yet. They were known as Schwarzschild singularities, named after Carl Schwarzschild, who found an exact solution to Einstein's equations in 1916. It described the gravitational field around a perfectly spherical, non-rotating mass. The mathematics was elegant, but it also contained a troubling feature, a region where space and time seemed to break down completely. Einstein disliked the idea. He believed that nature must somehow prevent such infinities from existing in reality. Enter Nathan Rosen, a young and mathematically gifted collaborator working with Einstein at the Institute for Advanced Study in Princeton. Together, the two began to explore whether relativity might contain a hidden symmetry, a way to connect two seemingly separate regions of space-time without resorting to a singularity. In 1935, their collaboration produced a paper titled The Particle Problem in the General Theory of Relativity. It introduced what would later be known as the Einstein-Rosen bridge. In essence, they had found a clever way to stitch together two sheets of space-time at what appeared to be the mouth of a black hole. Imagine taking two pieces of paper and gluing them together through a shared circular hole, a bridge linking two separate surfaces. To a physicist, this bridge wasn't made of matter or metal, but of geometry itself. It was a tunnel through the fabric of space-time connecting one universe, or perhaps two distant regions of the same universe, by means of a throat-like passage. The mathematics of this structure came directly from Einstein's own field equations. At first glance, it looked as though they had uncovered a possible solution to the cosmic shortcut question, a way for something to cross from one side of space-time to another without ever passing through the singularity of a black hole. For a brief moment, it seemed as if relativity had revealed a secret doorway built into its own logic. But reality, as always, had conditions. When they analysed the bridge in more detail, Einstein and Rosen realised that this connection would pinch closed too quickly for anything to travel through it. The geometry of space-time near the throat of the bridge was unstable. If one tried to send light or matter through, the passage would collapse instantly, sealing off both ends before any signal could cross. The two sheets were connected only in a mathematical sense, not in a way that could ever be used or observed. In that realization lay a quiet irony. The equations allowed such bridges to exist, but the universe seemed to deny them any practical use. Einstein had once again glimpsed how flexible the cosmos could be, and yet how firmly it resisted shortcuts. Even so, this strange fleeting structure captured the imagination of physicists. It suggested that the geometry of the universe could be more intricate than anyone had imagined. Not a simple expanse, but perhaps a network of hidden folds and tunnels invisible to ordinary perception. Although Einstein moved on to other questions, the seed had been planted. The idea of the bridge lingered in the background of theoretical physics, half forgotten until the mid-20th century, when a new generation of thinkers began exploring the deep consequences of relativity. Among them was John Wheeler, a man whose name would become almost synonymous with the wild frontier of space-time. Wheeler had a gift for turning complex mathematical ideas into language that fired the imagination. He coined the term black hole in the 1960s, giving an identity to the mysterious gravitational traps Einstein had once doubted could exist. And when he revisited the concept of the Einstein-Rosen bridge, he gave it a new, more vivid name, the wormhole. The image was simple but brilliant. Just as a worm might burrow through an apple, creating a tunnel from one surface to another, perhaps space-time itself could contain similar passageways. The analogy stuck, and so did the name. With Wheeler's framing, the old bridge idea gained new life. It was no longer seen as an obscure mathematical curiosity, but as a symbol of what relativity could make possible, at least in principle. Scientists began to ask fresh questions. Could such a wormhole exist naturally? Might the universe create them in the hearts of black holes or during the chaos of the Big Bang? And if so, could any be stable enough for information, or perhaps even a traveller, to pass through? At that point, these were still questions of pure theory, but the mere fact that Einstein's equations could describe such connections was thrilling. It showed that the structure of space-time was not limited to the three-dimensional space and single flow of time we experience. Instead, it hinted at a landscape that could fold, twist, and loop back on itself in ways that defied ordinary geometry. The beauty of the Einstein-Rosen bridge lies not in its physical feasibility, which remains doubtful, but in what it revealed about the nature of relativity. The theory didn't just describe how stars orbit or light bends. It described an architecture of reality so flexible that it allowed entire universes to be mathematically linked. It was a glimpse into the depth of the equations themselves, showing that space-time is a canvas far more dynamic than we can easily imagine. Einstein himself probably saw the bridge as a means of exploring how matter might be represented without singularities, a way to model particles as self-contained regions of curved space. For him, it wasn't a doorway for spaceships, but a clue about the fundamental unity of physics. Yet the fact that his mathematics allowed for such tunnels gave generations of scientists and dreamers permission to ask new questions. Questions about connectivity, causality, and the limits of the universe's design. There's something deeply human in that story. Two minds peering into a page of equations and discovering not just numbers, but architecture. A corridor connecting worlds that may not exist but which could. Einstein and Rosen may have closed their bridge almost as soon as they built it, but the thought of it has never really gone away. It remains a quiet testament to how mathematics can open a window into the unimaginable. And in that window, one can almost picture the universe not as an empty void, but as a living structure. A vast and elastic network where paths might sometimes meet, fold, or vanish altogether. The Einstein-Rosen bridge may never have carried a single particle from one side to another, but it carried human thought across a boundary just as profound. From the everyday understanding of space into the deeper realization that the universe itself might be more connected, more curved, and more mysterious than we ever dared to think. When Einstein and Rosen first uncovered their mathematical bridge, the equations seemed to whisper of possibility, a tunnel through space-time itself. But the universe, as it often does, had other plans. The bridge looked stable on paper, yet every attempt to imagine it as something physical quickly ran into trouble. Like a dream that dissolves when touched, the structure would collapse before anything could ever pass through. The heart of the problem lies in gravity's relentless nature. In a wormhole, gravity doesn't politely hold the tunnel open like a doorway. It crushes it from every side. The very curvature that creates the passage also conspires to close it. Imagine stretching a rubber band to form a loop. The more tension you apply, the more it tries to snap back to its original shape. A wormhole throat behaves much the same way. The immense gravitational pull of the surrounding masses drags space-time inward, tightening the tunnel until its walls meet in a catastrophic pinch. In the case of the Einstein-Rosen bridge, this happens almost instantly. If you could watch it form, which in reality you couldn't, it would appear and vanish faster than light could cross the distance between its mouths. It's as though space-time teases the idea of a shortcut, then seals it off before anyone can take it. Even light, the swiftest thing in the universe, never makes it through. And if light can't cross, nothing else can either. The mathematics behind this behavior is surprisingly unforgiving. When Einstein's equations describe the region around a black hole, they reveal something called an event horizon, the ultimate boundary. Once you cross that invisible surface, all possible paths lead inward, and the pull of gravity becomes absolute. In the Einstein-Rosen model, the wormhole's entrance lies inside such a horizon. To reach the other side, one would have to move faster than light, effectively escaping the very geometry of space-time. But relativity forbids that. The speed of light isn't just fast. It's the speed limit built into the universe's design. So even though the equations hint at a tunnel, the horizon around it makes the passage inaccessible. The two mouths of the bridge are not simply far apart. They're causally disconnected, meaning no signal, no matter how energetic or clever, can travel between them. From our side, the entrance to such a wormhole would look identical to a black hole. dark, uninviting, and one way only. Everything that enters vanishes beyond the horizon, never to return. To an outside observer, it's as if the bridge leads nowhere at all. The instability of wormholes comes from this dance between gravity and geometry. Gravity wants to compress, to bring everything together. To keep the tunnel open, something would have to push back, an internal pressure strong enough to counteract that collapse. In ordinary matter, there's no such force. The energy and pressure of normal particles always add to gravity's pull, not oppose it. This is why stars can't resist their own weight forever. Once the nuclear fire in their cores burns out, they shrink, collapse, and if massive enough, form black holes. A wormhole too feels that inward pull. Without a kind of matter that pushes outward instead of inward, it simply can't stay open. To picture the violence of that collapse, imagine standing near the throat of a wormhole as it begins to shrink. Not that anyone could survive such a place. The tidal forces would stretch and compress everything in every direction. Space itself would be flowing inward faster and faster until time and distance lose their usual meaning. From the outside, the collapse might look slow, almost frozen in time, because of relativity's distortions. But from the inside, it would be over in an instant, the geometry folding shut like a closing eye. Some theorists have tried to imagine ways to fight that collapse using clever modifications of Einstein's equations. What if negative energy could exert a kind of repulsive gravity, propping the tunnel open like invisible scaffolding? The idea is mathematically possible, but nature doesn't seem generous with negative energy. We see tiny hints of it in quantum experiments, but never in the quantities needed to balance a cosmic tunnel. So the wormhole remains a beautiful but unstable idea, a bubble of geometry that can't survive contact with reality. The difference between mathematical possibility and physical stability is subtle but important. Equations can describe many things that the universe never builds. In mathematics, you can draw a perfect circle. In reality, every circle has thickness, friction, and imperfection. Likewise, Einstein's equations can describe a space-time tunnel, but whether the cosmos actually permits it is another question entirely. The bridge may be lawful in theory, yet impossible in practice, like a blueprint for a building made entirely of fog. This interplay between what's allowed and what's real runs through all of physics. Nature often lets us glimpse ideas that exist only in her imagination, giving us just enough information to dream, but not enough to build. Wormholes fall into that category, tantalizing, mathematically valid, but physically self-destructive. They remind us that even in the deepest reaches of theoretical science, stability is the gatekeeper of existence. There's also a quiet symmetry to their failure. Gravity, which binds the universe together, also keeps it honest. The same force that sculpts galaxies and anchors planets refuses to let space-time fold too freely. It's as though the cosmos allows creativity, but only within the limits that preserve causality and consistency. A wormhole that stayed open without consequence would rewrite those rules, making faster-than-light travel possible and tearing at the logical fabric of time itself. The universe seems unwilling to take that risk. Einstein himself might have appreciated that restraint. He believed the universe was governed by harmony, not chaos, but a deep and elegant order. The fleeting nature of the Einstein-Rosen bridge could be seen as a kind of cosmic safeguard. It exists in the equations as a reminder of what could be, but collapses before it can create contradictions. In a way, the mathematics dreams, but reality wakes it up before it goes too far. If you could step back and look at the bigger picture, you'd see how this theme repeats itself across the cosmos. Stars shine because gravity and pressure are balanced. Galaxies form where attraction and motion find harmony. Even the expansion of the universe itself walks a fine line between growth and collapse. The wormhole simply strays too far from balance. Too much curvature, not enough support. And so, when we talk about why wormholes collapse, we're not just talking about physics, we're talking about the universe's temperament. It tolerates imagination but enforces discipline. It allows theory to stretch its legs, then gently reins it in with the laws of relativity and energy. In the end, that's part of what makes these ideas so beautiful. They remind us that our universe is both generous and cautious. Generous enough to let us dream of tunnels through space-time, cautious enough to make sure we can't fall through them by mistake. Somewhere in that balance lies the essence of science itself, the endless curiosity to ask, and the humility to accept the universe's quiet, graceful no. For much of the 20th century, wormholes existed as a kind of mathematical mirage, possible on paper, impossible in practice. The equations of general relativity allowed them, but those same equations swiftly crushed them closed. They appeared in the mind's eye for a moment and then vanished, sealed by gravity's firm hand. Yet physicists are a stubborn species. Faced with a forbidden structure, they didn't stop asking why, and, inevitably, someone began to wonder what if it could be kept open. That question reached a turning point in the late 1980s, when two theorists at Caltech, Kip Thorne and his graduate student Michael Morris, decided to take wormholes seriously, mathematically, at least. Their goal wasn't to build one, but to test the limits of Einstein's theory. They wanted to see what, if anything, the equations might demand to make a wormhole stable enough to traverse. The result was an answer both precise and fantastical. The universe would require something with the exact opposite properties of normal matter. In other words, to hold open a tunnel through space-time, you'd need matter that pushes outward instead of inward, something that resists compression, that curves space-time in reverse. This hypothetical stuff would have what physicists call negative energy density. Imagine placing it on a cosmic scale. Instead of adding weight to the universe, it would subtract it. In the presence of such material, gravity would behave strangely. Objects nearby would feel a gentle shove rather than a pull. A beam of light might bend the wrong way. The wormhole's throat, normally doomed to collapse, could be supported, like a bridge held up by a field of repulsion rather than tension. The idea sounds almost magical, but it emerges directly from the mathematics of relativity and quantum theory. Ordinary matter can never provide this effect. Its pressure and energy always enhance gravity's pull. But quantum fields are more mischievous. They fluctuate. They borrow energy from the vacuum, and occasionally, just occasionally, they can produce regions where the energy appears to dip below zero. That phenomenon is what gives scientists a faint glimpse of how exotic matter might behave. One of the clearest real-world examples comes from a subtle laboratory experiment known as the Casimir effect. When two ultra-smooth metal plates are placed extremely close together, just a few billionths of a meter apart, the quantum fields between them can't fluctuate freely. Only certain wavelengths fit in the narrow gap. Outside the plates, all wavelengths are allowed, creating a tiny difference in pressure. The result is a measurable attraction between the plates, as though the space between them contains slightly less energy than nothing itself. Physicists describe that region as having negative energy density. It's a delicate effect, small enough that it takes precise instruments to detect. The total force involved could barely nudge a speck of dust. But it proves a profound point. The concept of negative energy isn't science fiction. It's real, though confined to microscopic scales and fleeting moments. Nature allows it, but only in trace amounts. Scaling it up to the cosmic level required to keep a wormhole open would be like trying to inflate a soap bubble to the size of a galaxy without it popping. Thorne and Morris approached their work with scientific restraint. They weren't proposing that such wormholes existed. They were exploring what general relativity would require if one did. Their model was a thought experiment, a way to examine space-time at its most extreme and see whether the rules could bend without breaking. What they found was both exhilarating and humbling. The equations didn't forbid traversable wormholes outright, but the conditions were so specific, so precarious, that the cosmos itself seemed unlikely ever to satisfy them. To make matters even more intriguing, negative energy isn't just a theoretical curiosity. It plays a subtle role in other corners of physics. Certain quantum effects, like those responsible for Hawking radiation at the edges of black holes, also rely on temporary imbalances between positive and negative energy. These whispers of the quantum world suggest that space-time has a more complicated texture than we can see, one that might allow exotic phenomena under the right circumstances. But the gulf between quantum flickers and macroscopic engineering is immense. The universe may permit such phenomena in principle, but it gives no hint that they can be controlled or amplified. Physicists sometimes joke that the hardest part of building a wormhole isn't the math. It's convincing the cosmos to cooperate. Even if negative energy could be produced in significant amounts, it would need to be distributed precisely along the tunnel's interior, forming a perfectly balanced shell of repulsive gravity. A slight asymmetry, a momentary fluctuation, and the structure would snap shut faster than light could cross it. Keeping it open would require stability far beyond any technology or natural process we know. The phrase exotic matter endures because it captures both the wonder and the absurdity of the idea. It represents not fantasy, but the edge of legitimate theory, a placeholder for something nature might never create. The concept has nonetheless proved valuable. By studying the mathematics of exotic matter, physicists refine their understanding of energy, pressure, and the geometry of space-time. Even if no wormhole ever forms, the work illuminates how gravity and quantum mechanics intertwine, and how subtle the boundary between possibility and impossibility can be. Kip Thorne has often said that exploring far-fetched ideas is part of science's duty, to map the limits of the possible, even when the road stops at imagination. The search for a stable wormhole does precisely that. It teaches us how rigid and yet how elastic the laws of physics truly are. Einstein's equations contain entire universes within their symbols, and once in a while, they reveal paths that may never exist outside the mind. There's a quiet elegance in how the cosmos handles such bold proposals. It seems to allow them in theory, but guards against them in practice, like a careful artist approving the sketch but refusing the construction. Negative energy exists but only in whispers. The geometry of wormholes works beautifully, but only until gravity folds it shut. The universe gives us just enough to dream, then gently reminds us who's in charge. So while no one has ever seen a wormhole, and no hint of exotic matter has appeared in the night sky, the question remains one of the most profound in modern physics. Could space-time, under the right conditions, truly hold itself open, or will it always yield to gravity's insistence? The answer, for now, lies somewhere between the equations and the stars, a place where theory stretches to its limits and imagination learns to bow to reality. Every theory of the universe needs a few rules to keep it sensible. In physics, these rules are called energy conditions, guidelines that stop space-time from behaving too wildly. They're not laws in the same way gravity or electromagnetism are, but rather mathematical promises we ask the universe to keep. They say in effect that energy and mass should behave reasonably, that light should travel forward, not backward, that gravity should pull, not push, and that you shouldn't be able to make something from less than nothing. Most of the cosmos obeys these rules without complaint. Stars burn, planets orbit, and black holes bend light precisely the way the equations predict. But wormholes, as elegant as they look on paper, tend to break the rules entirely. To understand why, it helps to know what energy conditions actually are. In general relativity, Einstein's equations link the shape of space-time to the contents within it. Energy and mass tell space how to curve, and that curvature tells everything else how to move. But not every mathematical curve corresponds to something physically real. The energy conditions are like guardrails along the road of relativity. They make sure the solutions describe a universe that behaves, well, like a universe. There are several such conditions, each with its own slightly forbidding name. The weak energy condition, for instance, insists that the energy density seen by any observer must always be non-negative. In simpler terms, there should never be a place where energy drops below zero. The null energy condition requires that even light, travelling at its ultimate speed, should never encounter a patch of space-time with negative energy along its path. Then there's the dominant energy condition, which adds that energy should never flow faster than light, ensuring causality remains intact. These may sound technical, but they're really statements of common sense written in the language of mathematics. And then along came wormholes, cheerfully ignoring all of them. When you try to describe a traversable wormhole, one that could stay open long enough to cross, you find that its geometry demands exactly the kind of negative energy those conditions forbid. The throat of the tunnel must resist the inward pull of gravity, meaning space-time itself has to curve the wrong way. It's as though the universe were trying to build an arch without any stone, balancing a bridge on tension alone. Normal matter can't do that. It only adds weight. To keep the wormhole open, you'd need matter with pressure that pulls outward instead of inward, the very definition of negative energy density. Mathematically, this means that inside a wormhole, some of those energy conditions must be violated. The equations still work, but the universe would have to fill that region with something it has never been observed to create. That's why physicists call the stuff exotic matter, not because it's magical, but because it disobeys every polite rule matter normally follows. At first, that sounds like a deal-breaker. If energy conditions represent the universe's promise to keep things logical, then violating them should mean the idea collapses instantly. But the story isn't quite that simple. Quantum physics, mischievous as ever, refuses to play by classical rules. On very small scales, energy can fluctuate in strange ways, momentarily dipping below zero before bouncing back. These fleeting imbalances don't destroy the cosmos. They're part of how the vacuum itself behaves. This means the energy conditions, while excellent guidelines, aren't absolute. They work almost everywhere, almost all the time, but quantum mechanics allows them to be bent, just a little. The Casimir effect, for example, produces tiny pockets of negative energy between closely spaced metal plates. It's proof that the vacuum isn't perfectly obedient. Quantum fields seethe with fluctuations that, if averaged over long enough, behave nicely but in small regions and brief instants can rebel. Physicists sometimes describe this as the universe's quantum wiggle room. It's as if the cosmos, usually so disciplined, occasionally shrugs and says, "All right, but only for a moment." Those moments, however, are astonishingly short. The violations that quantum effects allow are minuscule and fleeting, nowhere near strong enough or long-lived enough to hold open a cosmic tunnel. Still, the very fact that the rules can be bent is encouraging in its own quiet way. It tells us that the laws of physics are not brittle, they have texture and flexibility. Einstein's geometry, combined with quantum uncertainty, produces a universe that's both orderly and playful, and in that narrow gap between what's forbidden and what's permitted lies the possibility, however faint, that under conditions far beyond our reach, something like a wormhole might exist after all. Of course, every time the math tempts us with that thought, nature seems to reply with a raised eyebrow. For every theoretical model that sneaks around the energy conditions, another calculation steps in to remind us that the universe probably won't cooperate. Quantum fluctuations that permit negative energy in one place must be balanced by positive energy somewhere else. The books always balance in the end. If space-time could talk, it might sigh patiently and say, "You can draw all the tunnels you like, but you'll still have to pay for them in full." It's a cosmic accounting system, with no loopholes big enough to slip a spaceship through. So, while the equations remain beautiful and full of potential, the universe appears content to keep wormholes in the realm of imagination for now. They serve as reminders of how far mathematics can stretch, and how firmly reality pulls it back. The energy conditions are the cosmos's way of keeping things grounded, even when the equations take flight. After all, physics has always been a conversation between creativity and constraint. The mind invents, the universe replies, and in this case the reply is gentle but firm. It seems the cosmos allows wormholes, but only on paper. If a wormhole truly connected 2 points in space-time, then it wouldn't just be a tunnel through space, it would also be a tunnel through time. And that simple realization is where things start to get beautifully complicated. The idea comes straight from Einstein's relativity. Time and space are woven together. What happens to one affects the other. If you distort space, you distort time along with it. So when theorists began to imagine traversable wormholes, structures that might, in principle, let light or even matter pass from one mouth to the other, they couldn't avoid noticing that such tunnels would also have their own internal clocks. And clocks, in relativity, are slippery things. They don't always tick at the same rate. Suppose you had a wormhole with 2 mouths. Leave one mouth here, quietly floating in space. Take the other on a journey, perhaps moving it close to a massive star where gravity runs strong, or accelerating it to near light speed before bringing it back. According to the rules of relativity, time at the travelling end would pass more slowly than at the one left behind. Astronauts experience this effect in a tiny way when orbiting Earth. Their onboard clocks run a fraction of a second slower than those on the ground. A wormhole, though, would magnify this difference enormously. When the 2 mouths are reunited, the clocks inside the tunnel would no longer agree. One would be older than the other, even though through the wormhole they remain directly connected. Step into the younger mouth, travel through, and you might emerge from the older one, arriving not just elsewhere, but elsewhen. The wormhole, in essence, has become a time machine. It's an extraordinary thought, yet the mathematics allows it. Nothing in Einstein's equations says you can't move the mouths this way. What changes is the geometry of space-time between them. One end now sits in a different temporal neighbourhood from the other, and the tunnel that joins them links those moments together. From the outside, the universe still obeys its usual rules, but for anyone inside the wormhole, time would loop and twist like a Mobius strip. Of course, such a possibility brings a crowd of paradoxes in its wake. Imagine sending a signal through the wormhole to the past, a message that warns yourself not to build the wormhole in the first place. If the warning succeeds, the wormhole isn't built and the message was never sent. But if it wasn't sent, the wormhole is built, which allows it to be sent after all. Logic begins to chase its own tail. These puzzles are known as causal loops. They sit at the edge of physics and philosophy, teasing the boundaries of what before and after even mean. In one scenario, an event might cause itself. In another, it might erase itself. Relativity doesn't forbid such structures outright. It merely describes them. The mathematics can handle the loop perfectly well. It's the human mind that struggles. Physicists have spent decades trying to understand whether the universe actually permits such time-tangled geometries. One camp argues that perhaps reality is self-consistent. Events can form loops, but they can never contradict themselves. The past, they say, is resilient. Any attempt to change it only ends up fulfilling it. You might travel back to stop an event, only to discover that your actions were the very cause of it. This idea, called the Novikov self-consistency principle, preserves logic but at the cost of free will. The future can influence the past, yet only in ways that maintain the story's coherence. The other camp is less forgiving. Among its most famous members was Stephen Hawking, who found these paradoxes intolerable. He suspected that nature itself must have a safeguard, a built-in defense against chronological chaos. In the early 1990s, he proposed what he called the chronology protection conjecture. It was his way of saying that time travel, while mathematically interesting, is physically impossible. According to his argument, as soon as a wormhole begins to act like a time machine, quantum effects surge out of control. Energy builds up around the tunnel's mouth, creating an enormous feedback loop of radiation that destroys the structure before it can be used. In Hawking's colourful phrasing, it seems there is a chronology protection agency which prevents the appearance of closed time-like curves and so makes the universe safe for historians. The conjecture remains unproven, but many physicists find comfort in its logic. It preserves causality, the fundamental rule that effects cannot precede their causes, and spares the cosmos from the headache of paradoxes. Still, the idea refuses to die quietly. Mathematically, there's no absolute barrier that prevents a wormhole from acquiring a time offset between its mouths. The equations simply describe what would happen if it could be stabilized, and they do so cleanly. It's reality that resists, not the math. If Hawking's conjecture is correct, then the universe quietly enforces causality by wrecking any attempt to break it. If he's wrong, then the laws of physics may tolerate far stranger patterns of cause and effect than our intuition allows. The fascination here lies not in building a time machine, but in understanding the subtleties of space-time itself. Wormholes, even as abstract ideas, test the edges of relativity and quantum theory. They force physicists to ask, how flexible is the timeline? How closely linked are cause and effect? And what exactly keeps history from unravelling into paradox? It's possible that the universe simply balances itself the way it always does. Gravity and expansion, creation and decay, everything in nature tends toward equilibrium. Perhaps time follows the same rule. Any attempt to distort it too severely triggers a correction, a surge of instability that restores order before chaos can bloom. In that sense, Hawking's Chronology Protection Agency isn't so much a bureaucratic metaphor as a poetic one. It expresses the quiet conviction that the cosmos, though playful with its geometry, remains loyal to logic. And yet, there's something almost comforting about the thought that the equations themselves allow such wild possibilities. They remind us that our understanding of time, this steady forward flow we all experience, is not the universe's only option. In the deep language of relativity, time can stretch, twist, and, under certain conditions, even fold back on itself. Whether or not nature ever permits such folds to exist, they remain part of the mathematics that describes everything we see. In the end, wormholes teach us something profound about humility. Even in pure theory, they confront us with questions that may never be answered. Does time truly have a direction, or is that simply the way we perceive it? Are paradoxes a flaw in our reasoning or a clue that the universe's logic is larger than ours? No one knows, but perhaps that's the charm of it, that space-time in all its elegance still keeps a few secrets tucked safely away. And if the universe really does have its own protection agency guarding the timeline, we can probably thank it for ensuring that curiosity, rather than chaos, remains the engine of discovery. Black holes are among the few celestial objects that truly deserve their reputation. They're not just mysterious or extreme, they're real. We have watched stars spiral into them, seen their gravitational pull sculpt the light of entire galaxies, and even captured the faint shadow one casts against the bright glow of falling gas. A black hole is not a hole in the usual sense, but rather a region of space-time where gravity has gone so deep into itself that escape becomes impossible. Not even light, the universe's speed champion, can climb back out once it crosses the boundary known as the event horizon. The event horizon isn't a solid surface. There's nothing to bump into. It's simply a line in space-time, a one-way threshold. Cross it, and every possible path forward leads inward, never out. Beyond that horizon, space-time curves toward a point of infinite density, a singularity, where the known laws of physics crumble. What happens there remains hidden, a question wrapped in the black hole's defining feature, its silence. For decades, physicists and philosophers alike have wondered what lies on the other side, if indeed there is another side. In the early years of relativity, when Einstein's equations were new, and their possibilities still being charted, scientists noticed something strange in the mathematics. The equations describing a black hole also contained a mirror image, a solution that looked the same, but with time running in reverse. This time-reverse twin was called a white hole. If a black hole is a cosmic sink, a place where matter and energy disappear, then a white hole would be a fountain, one that spews matter out and refuses to let anything in. Nothing could cross its horizon from the outside. Everything would be ejected outward, as though the universe itself were exhaling. It was an elegant counterpart, two extremes of the same geometry, one devouring, the other disgorging. Early researchers noticed that mathematically a black hole and a white hole could be joined together. The link between them formed what was called an Einstein-Rosen bridge, the same type of theoretical connection that later inspired the concept of wormholes. In this early picture, you could imagine falling into a black hole in one part of the universe and emerging from a white hole in another, or perhaps even in another universe entirely. It was a remarkable symmetry, a cosmic two-way street embedded in the logic of Einstein's theory. But that elegant picture didn't survive contact with reality. Actual black holes, the kind born from collapsing stars, don't behave like mathematical ideals. They are formed from ordinary matter that implodes under its own gravity, dragging space-time inward with it. There's no hint of a mirrored outlet at the other end. When you model this collapse more realistically, the white hole half of the geometry vanishes. What remains is a black hole with a singular core and no exit. Even if white holes did exist, they would be catastrophically unstable. Imagine an object that constantly throws out radiation and matter, but cannot absorb anything in return. Any slight disturbance, a stray photon, a grain of dust, would crash into its horizon, breaking the perfect symmetry required to keep it stable. The equations predict that the white hole would instantly collapse into a black hole, or simply evaporate into ordinary space. In a dynamic, messy universe filled with particles, fields, and random fluctuations, a pristine white hole would survive for less than an instant. That's why physicists believe white holes are unlikely to exist in nature. They are fascinating as a mathematical possibility, the reverse image of gravitational collapse, but nature prefers the irreversible flow of entropy. The arrow of time points forward, not back. Black holes align with that arrow. They consume, compress, and radiate energy away. White holes would require the universe to run in reverse, unwinding itself like a film played backward. Yet, for all their implausibility, white holes still spark curiosity. Some researchers have wondered whether the Big Bang itself might have behaved like one, an event where energy and matter erupted outward from a compressed state forbidden to re-enter. Others have suggested that on quantum scales, something resembling a white hole could briefly flicker into existence when black holes evaporate, releasing the information they once trapped. These are speculative ideas, but they show how a concept born purely from symmetry can keep evolving, adapting to new frontiers of theory. White holes also serve as a reminder of relativity's deeper beauty. Einstein's equations don't play favourites with time. If you reverse the direction of the arrow, the math still works. The same curvature that pulls everything inward can, in principle, push it out. What changes is not the geometry, but the universe's willingness to allow it. Reality, it seems, has a preference for one side of the coin. Black holes exist everywhere we look, at the hearts of galaxies, in the remnants of massive stars, and perhaps even in the earliest moments after the Big Bang. White holes, meanwhile, remain the ghosts of equations, haunting the edge of possibility but never crossing into the realm of observation. Still, the pairing has philosophical charm. Together they show how relativity unites opposites: gravity and expansion, motion and stillness, collapse and eruption. The same mathematics that describes the universe's most voracious objects also conjures their imaginary opposites. And in between those extremes lies the wormhole, a fleeting bridge, unstable but tantalizing, connecting the two. Black holes are the universe's consummate secret keepers. White holes, if they existed, would be the loudest storytellers imaginable, broadcasting energy without pause. That neither extreme appears in its pure form is perhaps the universe's way of keeping balance. Nature loves symmetry, but it also knows when to break it. What's left, then, is a quiet appreciation for how flexible the laws of physics can be. From one set of equations, we get two opposite visions, one real and consuming, the other imaginary and expelling. Both are valid solutions. Only one survives contact with the messy, evolving cosmos. White holes may remain forever theoretical, exquisite artifacts of mathematics, carved from the same logic that gave us black holes and wormholes alike. They remind us that equations can dream of possibilities the universe never builds, and that sometimes the most beautiful symmetries are the ones that exist only on paper. When we look out into space, it seems calm and continuous, a vast smooth fabric stretching endlessly in every direction. But physics has a way of revealing that appearances are deceiving. Just as a calm ocean seen from afar hides a roiling chaos beneath its surface, space-time too may be far from tranquil when viewed up close. Deep down, at scales smaller than any microscope could ever reach, the universe might not be smooth at all. It could be a restless sea of energy and geometry, flickering in and out of form. This idea, known as space-time foam, came from the mind of the physicist John Wheeler in the mid-20th century. Wheeler had already given the world the term black hole, and he had a knack for spotting poetry hidden inside equations. He imagined that if you zoomed in to the very smallest possible scales, distances around the Planck length, about 10 to the minus 35 meters, space-time itself would start to behave like a quantum object. It wouldn't be a calm, continuous surface anymore, but a jittery, bubbling foam of uncertainty. At such unimaginably small scales, the usual distinction between space and time begins to blur. Quantum mechanics tells us that energy fluctuates everywhere, even in a perfect vacuum. Virtual particles pop into existence, then vanish almost immediately. Wheeler extended that same logic to space-time itself. If the geometry of the universe can respond to energy, then it too must fluctuate when quantum uncertainty reigns. The result would be a kind of microscopic storm, regions bending and twisting, pinching off, reconnecting, a quantum froth rather than a smooth fabric. Within this foam, tiny wormholes might appear spontaneously. These would be the quantum cousins of the grand cosmic tunnels Einstein and others described, miniature bridges connecting different points of space-time for the briefest of instants. They would form and collapse so quickly that no signal, no particle, and certainly no traveller could ever use them. They are, in every sense, temporary wrinkles in the geometry of reality. It's almost impossible to visualize scales like these. The Planck length is to a proton what a proton is to the width of a galaxy. If an atom were blown up to the size of the observable universe, the Planck scale would still be smaller than a grain of dust inside it. That's the realm where Wheeler's foam would live, far beyond any direct observation, hidden beneath the fabric of all known physics. Although these wormholes would be fleeting and untraversable, they represent an idea of extraordinary depth, that space-time itself may have structure. Just as matter is made of atoms and light is made of photons, perhaps space is built from something more fundamental, a constantly shifting pattern of quantum geometry. The foam would be the scaffolding of the universe, restless and ever-changing, giving rise to the smooth, continuous space-time we experience at human scales. This vision of reality is more than poetic speculation. It lies at the heart of the search for quantum gravity, the theory that will one day unite general relativity, which governs the vast, with quantum mechanics, which governs the tiny. Wheeler's foam provided one of the first glimpses of what such a merger might look like. It suggests that space and time are not infinite continuums, but emergent properties that arise from something deeper. Physicists have since taken Wheeler's thought further. Some models of quantum gravity, such as loop quantum gravity, and certain versions of string theory, naturally produce structures that resemble this foamy landscape. In these pictures, space-time isn't a backdrop on which events unfold. It is the event constantly being rewritten by quantum fluctuations. Tiny wormholes, sometimes called quantum handles, may flicker in and out, linking neighbouring regions before collapsing again. Even though these wormholes would be smaller than subatomic particles and live for less than a trillionth of a second, they could, in principle, leave subtle effects on the larger universe. Some researchers have wondered if they might influence vacuum energy, the mysterious force driving the universe's expansion. Others have speculated that quantum entanglement, the strange connection between distant particles, could be related to microscopic wormhole links in space-time. These ideas remain speculative, but they capture the deep curiosity that Wheeler inspired. What makes the notion so compelling is its balance of chaos and order. On the one hand, space-time foam sounds like pandemonium, everything fluctuating wildly, constantly collapsing and reforming. Yet on the other hand, that chaos averages out to the serene, continuous universe we observe. The vast, predictable cosmos above us may be built from a foundation of absolute turbulence, a kind of quantum storm whose waves are so tiny and fast that we perceive only calm. It's reminiscent of watching sunlight on the surface of the ocean from high above. From a distance it glitters smoothly, a peaceful expanse. But dive beneath, and the water churns with invisible motion. Molecules colliding, currents twisting, eddies forming and fading away. Wheeler's space-time foam gives us a similar dual vision of the universe, smooth to the eye, seething beneath. And although no experiment has yet glimpsed this foam directly, the concept continues to guide theoretical physics. Quantum field theories suggest that energy at the Planck scale would be enormous, enough to warp space on the tinier scales. The very notion of distance may lose meaning there. Points in space-time could connect, separate, or merge in ways that defy classical geometry. It's a reminder that our familiar three dimensions and the ticking of time might be only approximations, like the apparent solidity of a table that's mostly empty space. Of course, no traveller will ever cross one of these microscopic wormholes. Even light, the fastest thing we know, would find them gone before it could complete the journey. They exist only as brief fluctuations like bubbles that form and burst before they can be named. But their existence, even as a possibility, is profound. They hint that the universe's complexity runs deeper than we can measure, that reality itself may be stitched together from impermanent connections, appearing and vanishing in an eternal quantum dance. John Wheeler once described the universe as a place where law without law reigns, where order emerges from the interplay of countless tiny uncertainties. His idea of space-time foam embodies that philosophy. It reminds us that even the emptiest vacuum is alive with structure, that the foundation of reality might not be smooth marble but living foam. And perhaps that's what makes the idea so quietly moving. The same physics that builds galaxies and bends starlight also ripples endlessly in the smallest crevices of space. The cosmos, it seems, is restless at every scale, infinite above and infinitesimal below. We stand somewhere in between, gazing outward and inward, knowing that beneath the calm surface of reality, the universe never truly sits still. In the long and often tangled history of physics, there are moments when two seemingly unrelated ideas suddenly meet, and in that meeting something extraordinary happens. One such moment arrived in 2013, when two physicists, Juan Maldacena and Leonard Susskind, proposed a daring link between quantum mechanics and the geometry of space-time. Their idea was summarized in a short equation that looks deceptively simple. ER equals EPR. At first glance, it reads like a cryptic bit of shorthand, but behind those 4 letters lies a bridge between 2 of the most mysterious concepts in modern physics: wormholes and quantum entanglement. The proposal suggested that every pair of entangled particles might, in a deep and abstract sense, be connected by a tiny, non-traversable wormhole. To unpack this, we need to step back. ER stands for Einstein-Rosen, the pair who first described a mathematical bridge between 2 regions of space-time, the wormhole. EPR stands for Einstein, Podolsky and Rosen, who, in 1935, published a different paper about something entirely distinct: quantum entanglement. In that work, Einstein and his colleagues argued that quantum theory must be incomplete because it allowed what he called spooky action at a distance, the instant correlation of 2 particles, no matter how far apart they might be. Einstein disliked the idea that information could leap across the universe faster than light, so he proposed that hidden variables must be at work behind the scenes. But over the decades that followed, experiments proved him wrong. Entanglement is real, and it's every bit as strange as it sounds. Measure one of a pair of entangled particles, and you instantly know the state of the other, even if it's on the opposite side of the galaxy. There's no signal travelling between them, just a shared quantum state that seems to transcend distance. Maldacena and Susskind realized that these 2 1935 papers, both written by Einstein and his collaborators, and both exploring the boundaries of connection, might actually describe the same underlying phenomenon. What if the mysterious link between entangled particles and the mathematical bridge between 2 regions of space-time were not just similar metaphors, but 2 sides of the same coin? The ER equals EPR proposal suggests that when 2 particles become entangled, the fabric of space-time itself forms a kind of hidden connection between them. Not a tunnel you could ever travel through, but a geometric bond at the quantum level. In this picture, entanglement and space-time are not separate ingredients of reality. They are deeply intertwined. The connections we see in quantum information might literally be the threads that hold space-time together. To be clear, this doesn't mean that every entangled particle pair harbours a wormhole that could be navigated. These wormholes would be what physicists call non-traversable. They can't be crossed. No matter, energy or signal can pass through them. They're more like mathematical echoes of entanglement than physical tunnels. Still, the idea is powerful because it offers a way to visualize something that always seemed almost supernatural. Instead of spooky action at a distance, perhaps what we're seeing is a kind of hidden architecture of space-time, a geometry that makes faraway points secretly adjacent in a deeper sense. In a way, ER equals EPR turns Einstein's own discomfort on its head. He once used the EPR argument to highlight what he thought was a flaw in quantum theory. Nearly a century later, that same argument may help explain how relativity and quantum mechanics fit together. The irony is exquisite. The very spookiness he distrusted might be the glue that binds the universe. To appreciate the boldness of this idea, imagine space-time not as a smooth, continuous sheet, but as a vast web of quantum connections. Each entangled particle pair would represent a tiny bridge, an Einstein-Rosen link, tying 2 regions together. On a large scale, those connections might weave the entire fabric of reality. Space, in this view, isn't a fixed stage. It's an emergent network built from quantum relationships. The beauty of ER equals EPR lies in how it unites opposites. Relativity deals with gravity, curvature, and the large-scale structure of spacetime, galaxies, stars, and black holes. Quantum mechanics deals with the tiny, jittering world of probabilities where particles exist in superpositions and uncertainty reigns. For decades, the two theories have refused to merge neatly. ER equals EPR offers a hint that the link between them might lie in information, in the way quantum entanglement organizes the geometry of space itself. In recent years, researchers have found hints supporting this vision in the mathematics of holographic duality, a framework in which gravity and a volume of space can be described by a quantum theory on the boundary surrounding it. In those models, the strength of entanglement directly shapes the geometry of the interior. Weaken the entanglement, and the space begins to tear apart. Strengthen it, and the space becomes smooth and connected. It's as if the universe's shape is sculpted by how much its parts are talking to each other. That's the sort of insight ER equals EPR captures. It's not saying that you can hop into an atom and emerge through another one across the room. It's saying that space-time itself may be the grand sum of all those entangled connections. The reason the universe is continuous and coherent might be because it's built on a foundation of quantum communication, billions upon billions of entanglements humming in harmony. This is, of course, still speculative. The ER equals EPR proposal remains a hypothesis, a tantalizing bridge between two powerful theories rather than a confirmed fact. But even as a metaphor, it's breathtaking. It reframes some of the strangest aspects of physics: quantum entanglement, black holes, the smoothness of space, as expressions of a single underlying principle. That connection is the universe's most fundamental property. It's also humbling. If ER equals EPR is even partly true, then every quantum interaction, every paired electron, every atom entangled with its environment adds a stitch to the cosmic fabric. The universe would not just contain relationships, it would be relationships woven together by information that transcends distance. Leonard Susskind once described this idea as a kind of poetry written in equations, and indeed, it's difficult not to feel that sense of wonder. The thought that every entangled particle might share an invisible geometric bond with its partner, that the quantum world and the structure of space-time could be one and the same, is both wildly abstract and quietly elegant. Whether ER equals EPR turns out to be a literal truth or merely a guiding metaphor, it has already changed how physicists think about the boundary between the quantum and the cosmic. It reminds us that science, at its best, doesn't just answer questions, it asks deeper ones. How connected is the universe really? What is distance if information can ignore it? And is space itself, in the end, just the shadow cast by entanglement? No one yet knows the answers. But if the universe does run on hidden connections, then perhaps every flicker of entanglement, every quantum handshake, is a reminder that even across the vastness of space, everything is already, somehow, linked. At some point in every discussion about wormholes, someone inevitably asks the practical question, could we ever build one? The idea is irresistible. If a tunnel through space-time could exist, surely a civilization advanced enough could figure out how to carve one open, a shortcut from here to there, from now to then. It sounds like the ultimate engineering challenge, something between a physics experiment and a work of cosmic art. But when physicists run the numbers, the universe quietly shakes its head. In theory, the recipe for a stable, traversable wormhole looks simple enough. Take two regions of space-time, connect them through a throat, and make sure the tunnel doesn't collapse. In practice, every step of that recipe involves problems so extreme that even our most optimistic theories falter. The first and largest issue is gravity itself. Space-time curves under the influence of mass and energy, and that curvature is what defines the wormhole's shape. To bend space-time enough to form a tunnel, you would need an enormous concentration of energy, far beyond anything the Earth or even the Sun could provide. And even if you could somehow gather that much energy, gravity would immediately try to crush the tunnel closed. To stop it, you'd need something to push outward from within, a force capable of counteracting the inward pull. This is where exotic matter comes into the story again, that elusive form of material with negative energy density, the only thing that could theoretically prop the throat open. Unfortunately, we've never seen more than the tiniest traces of negative energy, and those occur only in fragile quantum effects that vanish the moment you look too closely. The Casimir effect, for example, produces minute amounts of negative energy between two metal plates placed a few billionths of a meter apart. The effect is so small that it can barely nudge the plates together. To hold open a wormhole large enough for even a grain of dust to pass through, you'd need negative energy on the order of an entire star's output, multiplied many times over. In other words, you'd need a civilization with not only better physics but a much, much bigger energy bill than ours. Let's imagine, just for a moment, that such a civilization exists. Perhaps they've mastered quantum field manipulation, harnessed vacuum energy, and discovered how to sculpt space-time as easily as we shape metal. Even then, their engineers would face a terrifying list of design problems. A wormhole throat would have to remain stable against the tiniest perturbations. A passing particle, a stray photon, even the whisper of radiation could destabilize the geometry and cause it to collapse. Keeping the tunnel open would require constant fine-tuning, like balancing a pencil on its point in a hurricane. Then there's the issue of tidal forces. Inside a wormhole, gravity doesn't vanish. It stretches and squeezes along different directions. Anything passing through would be subjected to colossal distortions, strong enough to tear molecules apart. To make the journey survivable, the geometry would have to be sculpted so delicately that the tidal forces never exceed what a human body could endure. The precision required would make even atomic-scale engineering look sloppy, and that assumes you could even find a way to create the wormhole in the first place. General relativity provides solutions that describe wormholes, but it doesn't tell us how to make one from scratch. In Einstein's equations, wormholes simply exist as part of certain mathematical geometries. To create one would mean finding a way to manipulate space-time directly, folding it until distant points touched. The energies needed for such manipulation would dwarf anything achievable by particle accelerators or fusion reactors. The Large Hadron Collider, impressive as it is, moves subatomic particles with about the energy of a mosquito in flight. To meaningfully warp space-time, you'd need energies approaching the total mass of planets. Some speculative theories suggest that tiny, quantum-scale wormholes might form naturally in the frothing chaos of space-time at the Planck length. If such microscopic wormholes exist, perhaps one could be enlarged, gently inflated to macroscopic size using exotic matter. But that idea faces another hurdle. No known process can stabilize such a structure. The quantum fluctuations that create it would also destroy it almost immediately. Trying to inflate a microscopic wormhole might be like trying to blow up a soap bubble inside a hurricane. Even if a civilization somehow overcame every one of these obstacles, the energy requirements, the instability, the tidal forces, they would still face a final, formidable barrier: causality. As soon as a traversable wormhole could connect two regions of space-time, it would open the door to time paradoxes. Move one mouth of the wormhole relative to the other, and time at each end would drift out of sync. Step through, and you might not only travel across the galaxy, but into the past. The resulting feedback of radiation and quantum energy would likely destroy the tunnel before it could ever be used. It's as though the universe keeps an unspoken rule book that says no shortcuts, especially the kind that break logic. This doesn't mean that physicists have given up on exploring the concept. Wormholes remain valuable tools in theoretical research because they test the limits of what the laws of physics will tolerate. They show where general relativity collides with quantum mechanics, and how the universe might behave under extreme conditions. Even when the math leads to impossibility, the journey reveals where new physics might one day emerge. There are also playful thought experiments. What would happen if a wormhole mouth were placed near a black hole, or if quantum entanglement could mimic a wormhole connection? Could gravitational waves be used to detect one, if they existed naturally? These questions don't require us to actually build a wormhole, just to think about what reality allows and what it forbids. The answers help refine our understanding of space-time itself. Kip Thorne, who helped bring wormhole physics to mainstream attention, once said that the most valuable thing about such studies isn't the fantasy of interstellar travel, but the discipline they demand. Trying to build a wormhole, even on paper, forces physicists to confront the boundaries of known science, to see where our equations remain trustworthy and where they crumble. It's an exercise in both creativity and humility is exactly what the subject demands. The universe is not easily persuaded to break its own rules. For all our ingenuity, humanity still struggles to reach the nearest planet, let alone manipulate the curvature of space-time. We are engineers of small things, not cosmic architects. And perhaps that's just as well. The cosmos, it seems, is careful with its secrets. Still, it's hard not to admire the elegance of the idea. Somewhere within the mathematics of relativity lies a blueprint for tunnels that could, in principle, exist. Bridges that might link the farthest reaches of the universe in an instant. Whether or not anyone ever builds one, the fact that the universe's laws even permit the thought is astonishing. So could we ever build a wormhole? The honest answer is no. Not with any physics we know, and not with any technology we can yet imagine. But the question itself is worth asking, because it reminds us of how wondrously far those laws extend. They let us dream of shortcuts through space-time while keeping our feet quite firmly on the ground. And maybe that's their quiet lesson. The universe allows imagination to roam freely, as long as reality stays in charge. If wormholes exist somewhere in the universe, they would be spectacularly strange things to find. They wouldn't gleam like stars or glow like nebulae. They'd have no surface, no edge, no solid body to catch the light. A wormhole would reveal itself only through the way it bends the space around it, not by what it emits, but by what it distorts. Finding one, therefore, would be less like spotting a bright object, and more like noticing a flaw in the reflection on a perfectly still lake. Astronomers, always the detectives of subtlety, have considered how such distortions might appear. The most obvious signature would be gravitational lensing, a phenomenon already well known in astrophysics. When light from a distant star or galaxy passes near a massive object, the object's gravity bends the path of that light, acting like a lens. It can create arcs, rings, or multiple images of the same background source. We see this regularly around galaxies and clusters. elegant confirmations of general relativity. But a wormhole's lensing would be unusual. Instead of bending light from behind it in the usual way, a wormhole could, in principle, redirect light from a completely different region of the universe. To an observer, it might look as though a patch of sky contained the reflection of somewhere else entirely, like a cosmic window into another part of space. Imagine peering through a telescope and finding not a background galaxy distorted into a ring, but an entirely unfamiliar region of stars, a kind of gravitational mirage. Theoretically, such a pattern could be modelled. A traversable wormhole would produce a unique, symmetric lensing effect, sometimes described as a double Einstein ring. Two concentric circles of light formed by photons taking different routes around the tunnel's throat. Detecting that pattern would be an astronomer's dream, a signature unlike anything else in the cosmos. Unfortunately, the sky offers plenty of ways to imitate it. Massive galaxies, dark matter concentrations, and complex gravitational fields can create similar illusions. Nature, it turns out, is very good at faking wormholes. Another possible clue might come from orbital motions. If a wormhole acted as a gravitational well, objects near one could behave oddly. Their paths might shift or oscillate in ways that don't match the expected pull of a single mass. Some researchers have proposed looking at stars near supermassive black holes for just such anomalies. The black hole at the centre of our galaxy, Sagittarius A star, has become a natural testing ground. Astronomers have tracked nearby stars for decades, measuring their precise orbits with exquisite accuracy. If the central mass were secretly a wormhole, those orbits might show slight irregularities, deviations from the predictions of general relativity. So far they don't. The motions line up perfectly with what a black hole should produce. Radio telescopes and interferometers provide another way to search. When the Event Horizon Telescope captured the first image of a black hole's shadow in 2019, physicists immediately began wondering, what if that shadow had looked different? A wormhole's shadow, in theory, would have a distinct structure, perhaps brighter in the centre, or showing faint interference patterns where light from multiple paths meets. Such a discovery would have made headlines for centuries, but the image we saw matched the expectations for a rotating black hole, not a tunnel through space-time. Every photon followed rules already written in Einstein's book. This doesn't stop scientists from checking. Observational cosmology thrives on anomaly hunting, the search for things that don't quite fit. Could there be an object whose gravitational pull doesn't correspond to its visible mass? Could certain regions of the sky show mismatched redshifts, as if light had travelled a shortcut? Some teams have even examined gamma-ray bursts, wondering whether an unusual pattern of delay between signals could hint at light emerging from a wormhole's far end. The answer each time has been the same: no solid evidence, no hidden tunnels, just the familiar physics of extreme but ordinary objects. The challenge is that the universe is already full of dramatic behaviour. Black holes, neutron stars, supernova remnants, and quasars all produce phenomena that stretch our models of light and gravity. A wormhole would have to reveal itself against this noisy backdrop, and nature's existing catalogue of cosmic wonders leaves little room for ambiguity. Every time an odd lensing event or orbital pattern appears, conventional explanations rush in to fit it, and they fit remarkably well. Even the most speculative searches must respect the limitations of observation. We can't peer into every corner of the universe, nor measure every gravitational ripple in perfect detail. But what we can see obeys the laws we already know. No telescope, no detector, has yet recorded anything that truly requires a wormhole to explain it. When the data match ordinary gravity so precisely, the burden of proof for extraordinary geometry becomes monumental, and yet that doesn't make the search futile. Looking for something we don't expect often leads to discoveries we didn't imagine. The techniques developed for wormhole hunting, precision astrometry, interferometry, high-resolution lens modelling, have sharpened our ability to study everything else in the cosmos. The same observations that rule out wormhole confirm the existence of black holes, map dark matter, and refine our knowledge of cosmic structure. Even when the answer is no, the process itself advances our understanding. There's also a philosophical satisfaction in the pursuit. Every hypothesis we can test, even one that fails, strengthens the bridge between theory and observation. It reminds us that physics is not merely an exercise in imagination, but a dialogue with reality. The equations of general relativity are generous. They allow for all sorts of wondrous geometries. The universe, however, is more selective in what it builds. It's possible, of course, that wormholes do exist but hide beyond our reach, smaller than an atom, or disguised as ordinary black holes, or sitting quietly in regions we'll never observe. But until evidence demands their presence, the scientific position remains cautious. In the absence of anomalies that defy explanation, we must assume that space-time behaves as it always has, curved, beautiful and continuous, but without shortcuts. That humility is part of what makes astronomy so compelling. The sky invites both wonder and discipline. It tempts us with the possibility of cosmic doors, yet rewards us for careful skepticism. Even without proof of wormholes, we learn to see the universe with sharper eyes, to recognize that what we call empty space is anything but empty, and that every glimmer of light carries the story of where it's been. So far, every glimmer tells a familiar tale: galaxies bending light, black holes swallowing it, stars orbiting in perfect obedience to known physics. No mysterious tunnels, no echoes from elsewhere, no cosmic shortcuts. Just a universe following its own quiet rules. And maybe that's precisely what makes the search worthwhile. Because every time science looks for something extraordinary and finds the ordinary instead, it renews our respect for how extraordinary the ordinary truly is. The sky keeps its secrets well, and that, in its own way, is proof of how carefully the cosmos holds itself together. When we think about the shape of the universe, most of us picture something vast and straightforward, an infinite expanse stretching endlessly in every direction, sprinkled with galaxies and threaded with dark matter. But cosmologists know that space can be trickier than it looks. Geometry, on cosmic scales, can play subtle games. The universe might curve, loop, or even connect back on itself in ways that are almost impossible to imagine. And in those possibilities lies one of the most intriguing questions in modern science. Is space a simple, open canvas? Or does it hide deeper connections? Perhaps even something like a cosmic wormhole? To understand the question, it helps to realize that when cosmologists talk about the shape of the universe, they don't mean the shape of what it's expanding into. There's no outside to measure from. Instead, they are talking about the internal geometry of space itself. If you could set off in a straight line and keep going forever, would you eventually reach a boundary, or would you return to your starting point as if the universe were curved back on itself? This isn't science fiction. It's a question of topology. How space is connected at the larger scales. In everyday experience, geometry feels simple. A flat table stays flat. A sphere curves the same way everywhere. and a donut loops back on itself with a hole in the middle. But when we apply these ideas to the universe as a whole, things become more abstract. General relativity tells us that space-time curves in response to mass and energy, but it doesn't tell us what the overall shape must be. The equations allow for a range of possibilities. A universe that's infinite and flat, one that's closed like a giant three-dimensional sphere, or one with even stranger properties, where space wraps and folds through hidden dimensions, or where travelling far enough in one direction might bring you back from another. In the mid-20th century, as cosmology matured into a precision science, these ideas moved from speculation to observation. If the universe really did curve back on itself, light travelling through it might circle around, creating echoes or repetitions in what we see. Distant galaxies could appear more than once in different parts of the sky, their light looping through space on multiple paths. The cosmic microwave background, the faint afterglow of the Big Bang, could show repeating patterns, like a cosmic wallpaper where the same patch appears in several places at once. The cosmic microwave background, or CMB, is perhaps our most powerful tool for testing these possibilities. It's the oldest light in the universe, released when the cosmos was only about 380,000 years old. By mapping tiny temperature fluctuations in the CMB, scientists can infer the geometry of space itself. If the universe were curved like a sphere, the pattern of fluctuations would appear slightly larger. If it were curved like a saddle, they'd appear smaller. After decades of increasingly precise measurements from satellites such as COBE, WMAP, and Planck, the results have been remarkably consistent. On the largest observable scales, space appears flat, or at least so gently curved that any deviation is beyond our current ability to detect. But flatness doesn't necessarily mean infinity. Even a flat universe can have complex topology, like a video game world that wraps around at the edges. In that case, light travelling across the cosmos could loop back, creating repeated patterns in the CMB. Astronomers have searched exhaustively for such repetitions, matching circles or mirrored patches that might betray a universe with hidden connections. So far they've found none. The sky, it seems, contains no echoes of itself. That result suggests that space, as far as we can tell, is simply connected, meaning it doesn't fold or loop on itself in any detectable way. There are no giant shortcuts linking distant galaxies, no cosmic-scale wormholes curling space into a closed circuit. The universe is vast, continuous, and smooth. Its curvature, if any, is too subtle to see, and its boundaries, if they exist, lie forever beyond the horizon of what light has had time to reach us. Yet the mathematics still whispers of stranger possibilities. The same equations that describe a smooth, expanding cosmos also allow for more exotic topologies, spaces shaped like tori, Mobius strips, or even higher dimensional analogues of wormholes linking distant regions. These solutions aren't ruled out by general relativity, they're simply not observed. The universe we inhabit appears to have chosen simplicity, at least on the scales we can measure. But deep down in its quantum foundations, space may still possess the restless connectivity that John Wheeler once called space-time foam, a landscape where geometry is anything but simple. In a sense, wormholes represent the most extreme form of that connectivity. They are the geometric equivalent of shortcuts, hypothetical pathways that would let distant parts of the universe touch. On cosmic scales, if the universe had such connections built into its topology, it would mean that what looks far apart might actually be close in a deeper, higher dimensional sense. travelling in a straight line could, in theory, bring you back to your starting point. Not because space bends like a circle, but because it folds like paper. Cosmologists keep testing for such hidden folds because the idea, however remote, is too beautiful to ignore. Some theories of the early universe suggest that during the violent expansion known as inflation, space could have been twisted and knotted in ways that left subtle imprints on its structure. If wormholes formed in those first moments, they might have stretched or decayed with the universe's growth, leaving faint scars, perhaps patterns of gravitational waves or tiny irregularities in cosmic background radiation. So far, none have appeared, but the search continues with ever more sensitive instruments. Even without evidence for cosmic wormholes, the exploration of the universe's shape has revealed something profound, that geometry and destiny are intertwined. The shape of space determines how the universe evolves, how galaxies cluster, and how light travels across the cosmic web. A flat universe expands forever, growing colder and darker as time passes. A closed one could, in principle, reverse and collapse back into itself in a big crunch. An open one keeps stretching without end. Each possibility is a different kind of story written into space-time's architecture. For now, the story we read in the data is one of elegant simplicity. The universe appears flat, homogeneous, and connected in the ordinary way. No seams, no shortcuts, no repeated corners. It's a cosmos that behaves exactly as general relativity predicts, with light and gravity following the expected curves. Yet even in that simplicity there's mystery, because in the language of mathematics nothing forbids the other shapes. They remain in the equations, silent possibilities waiting beyond observation. Perhaps that's the universe's quiet compromise. On the human scale, it offers stability, a geometry that makes sense, predictable and consistent. But in theory, in the deep fabric beneath, it keeps its options open. The same physics that allows flatness also allows folding. The same laws that forbid wormholes in practice still describe them in principle. It's as though the cosmos itself understands the power of imagination, letting the equations dream of shapes that reality chooses not to build. And maybe that's enough. We don't need a universe filled with tunnels and loops to feel awe at its structure. The fact that it could have been that way, and yet instead formed the smooth, majestic expanse we see, is its own quiet wonder. The equations remind us that space could be more adventurous than it appears. But when we gaze at the night sky, clear, continuous, and immeasurably deep, we're reminded that even the simplest shape can hold infinite mystery. In physics, information is everything. It's what defines a system. Every particle, every field, every pattern of energy. In principle, if you knew all the information about the universe at one moment, you could, at least theoretically, predict everything that would ever happen. But the universe is clever. It hides its details behind horizons, inside singularities, and perhaps within wormholes. And as we reach for those hidden corners, we begin to learn not just about physics, but about the limits of knowing itself. Wormholes from the start have been about information. They are the promise of connection, a hypothetical bridge linking places, perhaps even times, that would otherwise be separated by impossible distances. In thought experiments, physicists imagine sending signals through them, light pulses, quantum particles, even entire objects of data. The appeal is obvious. If space-time can fold, maybe information can take a shortcut. But the deeper we look, the more the rules push back. Relativity tells us that nothing can travel faster than light. Quantum mechanics insist that information can't simply vanish or appear out of nowhere. Together, these two pillars of modern physics define a boundary around what can be known and transmitted. Wormholes fascinatingly sit right on that boundary. They seem to offer a loophole, a tunnel through the structure of the universe itself. Yet every time we test that loophole mathematically, it closes again. A traversable wormhole, if it existed, would have to allow signals to pass through without breaking causality. It would need to transfer information from one side to another, while still respecting the cosmic speed limit. In every stable model we've found, that's impossible. The geometry that keeps the wormhole open also prevents it from being used as a message channel. You can't use it to send a signal, a photon, or a secret to the far side. The tunnel exists, but it's mute, a silent connection that can be described but not used. That theme, connection without communication, reappears elsewhere in physics, most famously in the mystery of black holes. When a black hole swallows matter, it also swallows information about what that matter was. For decades, physicists assumed that information was lost forever behind the event horizon, erased from the universe. But quantum theory refused to accept that loss. According to quantum mechanics, information cannot be destroyed. It can only change form. This conflict between relativity's geometry and quantum theory's bookkeeping became known as the black hole information paradox. Stephen Hawking brought it to prominence in the 1970s when he discovered that black holes aren't perfectly black. They radiate faintly due to quantum effects near the horizon. That radiation, known as Hawking radiation, slowly drains the black hole's energy over immense timescales. But it seemed random, carrying no trace of what fell in. If that were true, the universe would be losing information, and that would mean the fundamental laws of physics weren't reversible after all. For years, the paradox stood as one of the deepest puzzles in theoretical science. But gradually, new ideas began to emerge. The concept of holography, which suggests that all the information inside a region of space can be represented on its boundary, offered a potential resolution. Information falling into a black hole might not be destroyed. It might simply be encoded on the horizon itself, hidden but not lost. And then came a strange twist. When theorists began exploring the link between entanglement and wormholes, the ER equals EPR idea, they noticed that the mathematics describing information flow across a wormhole was eerily similar to the mathematics of black hole evaporation. A wormhole in some models can act like a conduit that preserves information rather than erasing it. The connection between the two problems hinted that space-time geometry and quantum information might be two expressions of the same underlying reality. In that view, information is the true currency of the universe. Geometry might emerge from it, rather than the other way around. The fabric of space, the flow of time, even gravity itself could all arise from the way information is woven together through entanglement. In that sense, a wormhole isn't just a tunnel, it's a symbol of relationship, a metaphor for how information binds the universe into a coherent whole. But this perspective also deepens the mystery. If information is never truly lost, where does it go when hidden behind horizons or folded into microscopic wormholes? Some physicists argue that the information becomes scrambled beyond recognition, preserved in principle, but practically unreachable. Others suspect that quantum gravity might one day reveal a mechanism that transfers information back into the observable universe, in patterns so subtle we haven't yet learned to read them. Either way, The tension between what can be known and what is hidden remains at the heart of physics. Wormholes embody that tension perfectly. They are theoretically allowed, yet observationally invisible. They suggest possibilities that the universe refuses to demonstrate. They teach us that nature is not obligated to make its mechanisms accessible, no matter how beautifully the equations describe them. Information itself may obey a similar rule. In theory, every atom, every photon, every fluctuation in the quantum field encodes data about its history. But to retrieve that information, to truly reconstruct the past, would require more precision than the universe allows. Quantum uncertainty acts as a veil, ensuring that some details remain forever unknowable. The cosmos, in its wisdom, guards its privacy. This realization doesn't diminish science, it refines it. Physics has always been about boundaries, the speed of light, the uncertainty principle, the limits of energy and temperature. Each new limit we discover is both a restriction and an invitation. The edges of knowledge define the shape of curiosity. Wormholes, in that sense, are not failures of physics, but celebrations of it. Places where our equations reach the horizon of what can be tested. They also remind us that not everything true must be observable. The mathematics that describe wormholes, quantum entanglement, or information conservation are consistent and meaningful, even if no one ever peers through a tunnel in space. Science often advances by imagining what the universe could allow, then watching to see how reality responds. Sometimes it answers yes, sometimes no, and sometimes only with silence. That silence isn't emptiness, it's depth. It's the quiet reminder that the cosmos still contains mysteries vast enough to humble even our greatest theories. The notion of information, so precise, so seemingly absolute, turns out to lead us to the same conclusion wormholes do, that the universe may be perfectly logical, but not perfectly knowable. And perhaps that's the beauty of it. For all our equations and observations, for all our progress in understanding space and time, there will always be places where knowledge thins, where what is blurs into what might be. Wormholes live in that borderland, halfway between mathematics and mystery, connection and silence. In the end, they remind us of something simple and profound, that understanding doesn't mean possessing, and that the pursuit of knowledge is not about conquering the unknown, but learning to stand in awe of it. The universe may never reveal all its shortcuts, but it always leaves a path, a thread of curiosity that leads us forward, deeper into wonder and humbly aware that even in knowing so much, we have barely begun to know at all. Skepticism is sometimes mistaken for cynicism, as if scientists spend their days shooting down ideas just for sport. In truth, skepticism is one of the most creative forces in science. It's not the art of saying no. It's the discipline of asking, how do we know? It's what keeps the universe honest. And when it comes to something as spectacular as a wormhole, that discipline becomes essential. Because the truth is, scientists love wild ideas. They always have. Black holes were once dismissed as mathematical curiosities, gravitational waves were called unprovable, and quantum mechanics was viewed as philosophical nonsense. Every great discovery starts as a whisper from the impossible. But the difference between a good idea and a real one is evidence, and evidence is a demanding friend. If someone were to announce tomorrow that they'd found a wormhole, the scientific community wouldn't react with disbelief so much as with polite curiosity, followed by a barrage of questions. What did you observe? What instrument detected it? Could it have been lensing, a binary star, or just an oddly shaped cloud? How many people check the data? a claim that large would have to survive an avalanche of analysis before it could even begin to sound convincing. That's because extraordinary claims don't just need extraordinary evidence. They need repeatable evidence, and ideally peer review before bedtime. A single observation, however stunning, can always be a mistake. Nature has a long history of playing tricks on our instruments and our interpretations. A faint signal, a calibration error, or a coincidence of timing can easily masquerade as something new. Only when an effect reappears, measured independently by different teams using different methods across different wavelengths of light, does science begin to lean forward and pay attention. For a wormhole, the bar would be astronomical, quite literally. We'd need consistent, multi-layered proof, an object whose gravitational lensing can't be explained by any ordinary mass, whose radiation signatures defy the models of black holes or neutron stars, and whose behavior matches the predictions of a specific, testable theory of wormhole geometry. That theory would need to describe not only how the object behaves, but why it doesn't collapse, and it would need to do so without breaking the other well-established laws of physics. Only then would scientists even begin to whisper the word wormhole out loud. And even then, skepticism wouldn't disappear. It would intensify, because confirmation in science isn't about one big yes. It's about hundreds of smaller yeses that all point to the same conclusion. The universe is vast, and so are our imaginations. To tell the difference between what exists and what enchants us, science demands repeatability, consistency, and humility. That humility has deep roots. History is full of discoveries that looked revolutionary at first, and then quietly evaporated under scrutiny. In the 19th century, astronomers once thought they'd discovered a new planet called Vulcan, orbiting closer to the Sun than Mercury. It turned out to be an illusion. In the 1960s, a strange radio signal was jokingly nicknamed LGM-1, short for Little Green Men. It became the first detection of a pulsar. In both cases, curiosity wasn't the problem. The problem was that nature can mimic wonder a little too well. So when a physicist looks at a supposed wormhole candidate, skepticism isn't about doubt for doubt's sake. It's about respect. Respect for the data, for the history of mistakes, and for the rigor that turns a hypothesis into knowledge. Good science doesn't rush to be right. It takes its time to be sure. Even Einstein's own predictions had to wait for confirmation. His theory of general relativity was elegant, but it wasn't accepted until astronomers observed starlight bending around the Sun during a solar eclipse in 1919. The same goes for gravitational waves predicted in 1916, and detected almost exactly a century later by the LIGO Observatory. The long wait wasn't due to disbelief. It was due to care. Science wanted to be certain, and certainty, in this business, comes only from evidence that survives every attempt to destroy it. A good scientist tests an idea the way a bridge engineer tests a design, not by admiring its beauty, but by trying to shake it until it breaks. If it stands, you can trust it. If it doesn't, you've learned something even more valuable. Where not to step. It's also worth remembering that skepticism doesn't extinguish wonder, it refines it. The more carefully we question, the more clearly we see what's truly remarkable. The first image of a black hole, for instance, was met with cautious excitement, not uncritical celebration. Scientists knew how easily data could be misinterpreted, but as the results were checked, recalculated and confirmed, the wonder became stronger, because now it was earned. If wormholes are ever found, that same process will unfold. At first, every scientist on Earth will assume it's something else. A trick of gravity, a lensing artifact, an illusion caused by overlapping galaxies. Then, as the evidence holds, as models predict the same behavior, and as new observations agree, the skepticism will turn into awe. And that awe will be deeper, not in spite of the doubt, but because of it. Humour helps too. In science, skepticism can be serious work, but it's also an act of joy. The peer review process may not sound glamorous, but it's where the most productive arguments in the universe happen. A researcher presents their findings, others poke holes in them, and out of that friction comes clarity. Sometimes it happens late into the night, which is why the best rule of modern physics might be no extraordinary claims without peer review before bedtime. At its core, scientific skepticism is simply curiosity with guardrails. It's the understanding that belief must never outrun evidence, and that evidence must be willing to withstand attack. It's how science keeps its imagination in check while letting it roam freely. The same people who dream of wormholes and cosmic shortcuts are the ones who also demand proof before celebration. That balance, the coexistence of wonder and restraint, is what gives science its credibility. It can be tempting, especially with topics as captivating as wormholes, to let excitement turn into certainty. But true discovery is patient. The cosmos doesn't hand out secrets easily, and we wouldn't appreciate them as much if it did. When scientists stay skeptical, they're not shutting the door on mystery. They're making sure that when that door finally opens, we know it's real. And maybe that's the quiet beauty of it all. Skepticism is the rhythm that keeps science honest, a steady heartbeat beneath the noise of excitement. It doesn't crush dreams, it protects them from collapsing under their own weight. Without it, every bright idea would drift away like starlight through fog. With it, even the wildest theories have a chance to become truth. So the next time someone imagines a tunnel through space-time, a bridge between stars, or a shortcut to another universe, the proper response isn't disbelief, it's curiosity, tempered with care. Because in the long run, skepticism isn't what slows discovery. It's what ensures that when discovery arrives, it lasts. There's something deeply human about falling in love with ideas that may never exist. From the first sketches of flight to the equations describing time travel, imagination has always outpaced what the universe allows. And yet that leap ahead is how science moves forward. Wormholes are perhaps the most elegant example of this. Even if no one ever finds one, or builds one, or sails through one, the very act of thinking about them has reshaped the way physicists understand reality. At first glance, a wormhole seems like a fantasy problem, the kind of thing you'd doodle on the margins of a textbook when daydreaming about shortcuts to distant galaxies. But within physics, they are more than cosmic daydreams, they are tests. Every time a physicist writes down the equations for a wormhole, they're testing the boundaries of Einstein's general relativity and asking, how far can these rules stretch before they break? And sometimes, in exploring where the rules fail, the rules themselves become clearer. Wormholes have forced scientists to think about gravity not just as a gentle curve of space, but as a dynamic structure that can twist, connect, and almost tie itself into knots. They've shown that Einstein's equations can describe things far stranger than planets orbiting stars. They can describe entire geometries that fold space in on itself, the mathematical version of origami made out of space-time. But perhaps the most valuable part of wormhole physics is how it has nudged scientists toward unifying two great frameworks of knowledge: general relativity, which explains the large-scale curvature of space and time, and quantum field theory, which governs the tiny fluctuations of particles and forces. These two pillars of modern science describe the universe beautifully in their own realms, yet they resist merging into one coherent picture. Wormholes, sitting at the crossroads of both gravity and quantum effects, serve as natural laboratories for testing ideas that might one day bring them together. For instance, when physicists explore what might keep a wormhole open, they have to account for exotic matter and negative energy, concepts that draw directly from quantum field theory. In doing so, they discover how quantum effects could subtly influence the geometry of space-time. These calculations, though purely theoretical, help refine our understanding of vacuum energy, quantum fluctuations, and the interplay between energy and curvature. They reveal where relativity holds firm and where quantum mechanics begins to whisper, "Not so fast." Even when those whispers turn into contradictions, the friction is valuable. Every failed wormhole model teaches physicists something about what the universe won't allow, about which energy conditions are sacred, which symmetries must remain unbroken, and which shortcuts lead to paradoxes. In other words, wormholes are a way of reverse engineering reality. By asking how to build the impossible, we learn more about what keeps the possible stable. This method of learning through impossibility has deep roots in science. Centuries ago, mathematicians explored imaginary numbers, quantities that couldn't exist in the usual sense, and in doing so, unlocked entire branches of physics and engineering. The same goes for wormholes. Even if they remain mathematical fictions, they are useful fictions. They serve as scaffolding for ideas too large to hold in one theory. Some of the most fertile discussions in modern theoretical physics have grown directly from wormhole research. Concepts like holographic duality, quantum information flow, and the nature of black hole entropy all intersect with the mathematics of space-time bridges. The ER equals EPR proposal, the notion that entangled particles might be connected by microscopic wormholes, wouldn't have existed without the earlier groundwork of wormhole theory. These connections reveal something profound, that thinking about impossible tunnels through space can lead to genuine breakthroughs in understanding how reality connects itself. Wormholes also highlight one of science's most beautiful contradictions, that equations can describe things the universe might never build. The mathematics of general relativity is incredibly permissive. It allows for black holes, time loops, expanding universes, and geometries so exotic they could make a topologist dizzy. Nature, by contrast, is more selective. It seems to have looked at the cosmic menu and ordered only a few of the options. But even the dishes it didn't choose still tell us what could, in principle, exist in a universe governed by the same laws, and so physicists keep sketching those forbidden geometries, not because they expect to find them, but because doing so sharpens their understanding of the laws themselves. Wormholes are like the universe's unbuilt prototypes, beautiful blueprints drawn to test the edges of possibility. There's also a kind of poetry in how these theoretical constructs invite collaboration between imagination and precision. To model a wormhole, you need creativity to picture the shape of space folding in ways no one has ever seen, but you also need mathematics strict enough to keep fantasy from floating away. It's an art form disguised as science, geometry as storytelling. For younger scientists, wormholes are a gateway into deeper thinking. They spark the question, what does it mean for something to exist mathematically but not physically? And for seasoned researchers, they remain a constant reminder that progress depends on daring to ask the unanswerable. Many breakthroughs in physics began as jokes or curiosities. The first mention of black holes, after all, was made with a hint of irony. Yet curiosity, once taken seriously, has a way of becoming destiny. Even the failure to find wormholes tells us something profound about nature's character. The fact that space-time can be so flexible in theory, yet so disciplined in practice, suggests that the universe values stability over spectacle. It shows us that the cosmic stage is intricate enough without needing shortcuts between the acts. And that balance between what's allowed by mathematics and what's chosen by reality is what keeps science endlessly interesting. In a way, studying imaginary wormholes is an act of gratitude. It's a celebration of the human urge to explore even when the destination doesn't exist. Each equation is a conversation with the cosmos, a polite inquiry into how it handles the extraordinary. And even when the answer is no, it's delivered with elegance. So while we may never step through a wormhole, we can thank them for everything they've opened in our understanding. They've shown that curiosity itself can bend the fabric of knowledge, that by chasing what might be, we refine our grasp of what is. Perhaps that's why scientists keep returning to the topic, generation after generation. Because somewhere in those graceful equations lies a reminder of what makes physics so endlessly human. The joy of wondering, the courage to imagine, and the humility to accept that some bridges exist only in thought, yet still manage to carry us a little closer to understanding the universe we call home. There's something timeless about the idea of a bridge. Humans have always built them, across rivers, between islands, through mountains, each one a quiet act of defiance against distance. In the language of physics, a wormhole is the ultimate version of that dream. It's the bridge written into the geometry of space-time itself, the mathematical expression of our wish to connect what seems forever apart. Even if no one ever crosses one, the idea captures something enduring about the way we think, the way we reach. From the moment Einstein and Rosen sketched their theoretical tunnel in 1935, wormholes have existed as symbols of curiosity, where mathematics touches wonder. They remind us that the human mind is itself a kind of bridge, capable of spanning enormous conceptual distances. One moment, we stand grounded in measurable reality, tracing the orbit of a planet. The next, we're imagining tunnels between galaxies, connecting infinities through equations drawn on a chalkboard. Physics has a habit of turning dreams into definitions. Gravity became geometry. Light became both wave and particle. Time became a dimension that flows with space. Wormholes belong to that same lineage, an idea that grew from metaphor into mathematics, then paused just short of reality. In doing so, they carved out a space where imagination and precision coexist. They show that even the most speculative concepts can be explored rigorously, that curiosity and calculation can share the same quiet room. And perhaps that's why the fascination endures. To study wormholes is not just to chase a cosmic shortcut, it's to ask how far the human mind can go in describing a universe that seems determined to remain just out of reach. They're the places where equations become philosophy, where geometry becomes poetry. They whisper of symmetry and connection, of a cosmos that might fold in on itself like a thought circling home. Even without evidence, wormholes have changed how we see space and time. They've deepened our understanding of general relativity, guided our exploration of quantum theory, and inspired entire generations to look upward and wonder. They've blurred the line between what's real and what's possible, between the physics we can measure and the beauty we can only imagine. That's no small achievement for something that may never physically exist. In their way, wormholes embody one of science's quiet truths, that progress doesn't always mean arrival. Sometimes the journey itself, the act of following curiosity wherever it leads, is the real discovery. When physicists work on wormholes, they're not just hunting for cosmic tunnels, they're exploring the nature of knowledge itself. What does it mean to describe something we might never observe? What does it mean to map the shape of reality when that shape might include paths forever closed to us? Questions like these are what keep science alive. They remind us that uncertainty isn't a failure, it's a form of freedom. The unknown gives exploration its purpose. Every wormhole equation, every failed attempt to stabilize one, every simulation that collapses under the weight of its own gravity, all of it brings us closer to understanding what space-time really is and what our minds are capable of imagining within it. And maybe that's the quiet brilliance of the wormhole story. It's not just about bending the universe, it's about bending perspective. It invites us to think in 4 dimensions, to see time as geography, to imagine a cosmos where paths cross not by motion but by thought. It's a humbling reminder that the same laws of nature that sculpt galaxies also leave room for speculation, for dreams hidden between the variables. There's also something deeply comforting in the symmetry of it all. The equations that gave us black holes, those ultimate traps of light and matter, also gave us wormholes, their graceful opposites. One devours, the other connects. One marks an end, the other a possibility. The two are twins born of the same mathematics, showing that even within the strict order of physics, opposites coexist, balance each other, and complete the picture. Through them, we glimpse the larger nature of space-time, not a cold void, but a living fabric woven with potential. Every mass, every photon, every quantum fluctuation is part of that weave, pulling and stretching in patterns that shape the cosmos. To think about wormholes is to sense the elasticity of that fabric, to realize that the universe isn't rigid but creative, capable of forms we've only begun to imagine. And yet, after all the theories and debates, the most profound thing about wormholes might be what they leave unresolved. They remind us that there are places our understanding cannot yet reach, and perhaps never will. They invite humility, not the kind that gives up, but the kind that marvels at how much remains to be explored. The unknown isn't an obstacle, it's the horizon that keeps moving as we walk toward it. In that way, wormholes mirror the act of science itself, a never-ending attempt to connect islands of knowledge across an ocean of mystery. Each discovery is another bridge, built carefully between what we know and what we still dream about. Some bridges stand, others crumble under scrutiny, but everyone teaches us how to build the next. So even if wormholes stay in the realm of thought, pure geometry, untouched by matter, they've already done their work. They've joined curiosity with discipline, wonder with mathematics, and possibility with restraint. They've shown that the greatest power of science isn't in proving everything true, but in imagining what could be true, and then testing those dreams against the patient silence of the cosmos. When we look up at the stars and imagine invisible bridges linking them, we're doing what our species has always done, reaching across distance with thought. Whether that distance is physical or conceptual hardly matters. The real wormhole, the one that truly exists, is the connection between curiosity and understanding. And perhaps that's how every great question ends, not with certainty, but with awe. The universe may never reveal a tunnel through its heart, but it has revealed something even more extraordinary, that we can think of one, describe one, and find meaning in the attempt. Somewhere between imagination and observation, Between geometry and wonder lies the horizon where science and dreaming meet, a place vast enough for both. So, are wormholes real? It's the question that lingers after all the theories, all the thought experiments, and all the quiet wandering beneath the stars. In a sense, the answer depends on what we mean by real. In the language of mathematics, wormholes are perfectly real, consistent, logical, and beautifully described by Einstein's equations. They emerge naturally from the same geometry that explains gravity, light, and the motion of planets. On paper, they are flawless. But in the physical universe, in the realm of matter and measurement, they remain unproven. Elegant possibilities that nature has not yet chosen to reveal. That duality is what makes them so fascinating. A wormhole exists where imagination and physics meet, a place where the laws of space-time say maybe, and human curiosity rushes in to explore that possibility. For nearly a century, scientists have followed those equations through every twist and curve, not because they expect to find tunnels through the stars, but because doing so teaches them how space-time itself behaves. Even if wormholes never appear in the sky, they've already reshaped how we think about distance, time, and connection. In a way, the search for wormholes has become a mirror for science itself, a reflection of how we reach beyond what can be proven, guided by curiosity but tethered by reason. Every attempt to understand them sharpens our understanding of the universe's rules. Every equation that breaks under its own weight reminds us that nature is both generous and strict, willing to show us glimpses of its structure, but never giving away its deepest secrets easily. And yet, the beauty lies not in the answers, but in the questions. Wormholes invite us to ask how far the universe can bend without breaking, how time and space weave together into one fabric, and whether there might be patterns beyond what we can observe. Those questions don't demand solutions, they demand patience, the kind of quiet curiosity that science depends on. For now, the evidence is clear. No telescope has glimpsed one, no gravitational lens has betrayed their presence, and no observation has demanded that they exist. But the absence of proof is not the same as the proof of absence. The universe has always hidden more than it shows. There was a time when black holes were thought impossible, when exoplanets were speculative, when gravitational waves were just mathematical noise. Step by step, patience turned impossibility into understanding. Maybe wormholes will follow that same path someday, or maybe they'll remain purely theoretical, existing only in equations and imagination. Either way, they've already earned their place in the story of science. They remind us that progress isn't only about discovery, it's about perspective. The value of a theory lies not in whether it's real, but in what it helps us see. Even a purely mathematical wormhole offers a quiet kind of truth. It tells us that the universe is flexible enough to contain such beauty, that its laws are broad enough to permit the idea of bridges through space-time. It tells us that our minds are capable of reaching across that vastness and describing it with precision. That in itself is extraordinary, that the same species that light campfires under the stars can also write down equations that might, in another universe, connect those stars. Perhaps that's what makes wormholes so deeply peaceful to contemplate. They're impossible, yet plausible, distant, yet familiar. They stand as symbols of human imagination, not as portals to other galaxies, but as reminders of how far thought itself can travel. Science doesn't need final answers to offer comfort. Sometimes, understanding what we don't know brings its own kind of clarity. The mystery of wormholes isn't frustrating, it's freeing. It shows that curiosity has no ceiling, that we can explore forever without ever exhausting the wonder of what remains unexplained. And maybe that's how it should be. A universe where everything was known would be smaller, colder, quieter. The one we inhabit is alive with possibility, filled with open questions, untested ideas, and half-seen horizons. Every unproven theory is an invitation, every unsolved equation a gentle nudge to keep looking. So are wormholes real? They are real as mathematics, unproven as physics, and invaluable as inspiration. They belong to that rare category of ideas that live comfortably between reality and imagination, firm enough to study, fragile enough to dream about. Somewhere out there, light still travels through the deep curvature of space, bending around stars, slipping past black holes, tracing the invisible geometry of the cosmos. It follows the rules perfectly, revealing the universe not as static but as fluid, forever stretching, folding and unfolding. Every photon, every wave, every glimmer in the dark is a small reminder that reality itself is more intricate than we can yet measure. Maybe there are no tunnels hidden among those curves, no shortcuts between distant galaxies, or maybe there are quiet, imperceptible bridges we've simply not learned to see. Either way, the mystery endures, and so does the wonder. As you drift into rest, let that thought linger. Somewhere, far beyond sight, the universe continues to unfold its secrets, not in haste, but in its own patient rhythm. Each discovery, each question, each spark of curiosity brings us a little closer, though never all the way, and that's enough.